Section 5.3 will deal with how to predict the shapes of the Lewis dot structures that you drew in Section 5.2, molecules in 3D. So hopefully by now you know that bonds are made up of pairs of electrons, and those electrons are negatively charged, and that negatively charged particles repel one another. So molecules will arrange themselves in three-dimensional structures so that those bonds are as far apart as they possibly can be from one another. The theory that explains this process is called vsepr, valence shell electron pair repulsion. Take the first letter of each word, vsepr. Valence shell, outer shell electrons, those are the ones that are going to be involved in the bonding process. Electron pair, we're talking about the bonds between the atoms, which are made up of electron pairs. Repulsion, the fact that the electron pairs will repel each other. Theory, which is our attempt to explain this behavior that we see. The way that I'm going to teach you to predict shape is by coding the Lewis dot structure. A code will consist of 2 to 3 letters, always an A and a B, and sometimes an E. The A will stand for the central atom in the Lewis dot diagram. The B will stand for the number of bonding atoms off the central atom, and the E will stand for any number of lone pair electrons coming off the central atom. So let's take a look at our first shape, which is called linear. If we take a look at the first picture, you will see that that is of molecule BeCl2. So we have Be in the middle, and we have 2 chlorines on either side. Of course, remember that there are lone pair of chlorine around this diagram, but there are none on beryllium. If we code this, you will see that the central atom is A. There are 2 terminal atoms, which are bonding atoms coming off the central, so that will be AB2. And that's the code that will correlate to the shape of linear. Notice that the 2 bonding atoms are 180 degrees apart from one another. That is as far as they can get from one another in 3-dimensional space. So any molecule that will be coded as an AB2 will be linear in structure. You will also notice that down at the bottom there is a second formula, hydrogen chloride, and it consists of hydrogen and chlorine. And I'm going to draw in the valence electrons around the chlorine. This time you can see that it's just a 2-atom molecule. Any 2-atom molecule will always be linear in shape. We don't code this one because there is no central atom. You just need to remember that any 2-atom molecule will be linear. Alright, the next shape that we're going to look at is trigonal planar, and we'll focus on the chemical formula of boron trifluoride, BF3. Now boron is going to be in the middle, and we're going to have the 3 fluorine atoms around the boron. I'm going to draw in my lone pair of electrons here. If we were to code this, you would see that there is a central atom, which will be A, and there are 1, 2, 3 bonding atoms. No lone pair coming off the central, just 3 bonding atoms. And AB3 is going to correlate to the shape of trigonal planar. And the terminal atoms are 120 degrees apart from one another. And that's as far apart as they can get from one another. If we take a look at the picture in the middle, you'll see that the way that the bonds have been drawn are with wedges and dashed lines. And those are to help you see the 3 dimensions. Usually when you draw a wedge, that would be a bond coming towards you, and the dashed lines would be bonds going away. You do not have to do that. You can just draw the bonds like you see right here. What I do want to point out to you is when you drew this structure, you probably drew it like this according to the rules in the last section. So what our focus is in this section is taking that Lewis dot diagram and coding it. There's my A, and there's my 1, 2, 3 bonding atoms to get AB3, Now, knowing that's trigonal planar, I'm going to go ahead and I'm going to draw that structure in the triangular shape that you see in the middle. The next shape that we're going to look at is tetrahedral, and we will focus in on carbon tetrahydride. Now, once again, if you were to draw this using the Lewis dot rules from section 5.2, you would have ended with that structure. If we code that structure, we have an A, and we have 4 bonding atoms coming off that central atom. An AB4 will always correlate to a tetrahedral shape, and three-dimensionally, that means that these terminal atoms are now about 109.5 degrees apart from one another. The correct way to draw the structure would be then to just kind of shift the hydrogens down like this. And you can see that in the original diagram referencing the shape. Now, this is the only structure where I will let you actually draw it a little incorrectly, because when we get to our next section where we have to predict polarity, it's going to be easier to predict the polarity off of this structure versus this one, the correct one. So just understand that the tetrahedral shape really does look like the one on the right, but I will let you draw it kind of like a T over here just for future purposes. The next shape we want to look at is the trigonal bipyramidal shape. And if you take a look at the picture of PCl5, you'll notice that there are 10 bonding electrons, or 5 pairs. And that exceeds the octet. Now, you've been told that elements want to maintain an octet. What I didn't tell you is that there are some elements that can exceed the octet. Any nonmetal in period 3 or higher can have more than 4 bonding pairs. It can have 10, 12, 14, or so forth, because it has that D sublevel available to them to house the electrons. So the trigonal bipyramidal shape is the first one we see that is kind of breaking that rule that we were holding true with in the previous shapes. So this would be something like PCl5. And the way that we draw this is we make 2 of the atoms linear, and then we make the other 3 in a trigonal pyramidal shape. And the angles that we're going to see here are really 90 degrees between some of the chlorine atoms, and then sometimes you're going to see the 120 degrees between some of the other chlorine atoms. Of course, you'd have to imagine this in 3-dimensional space. Right now we're just doing it 2D. But in any case, you can see that there is a central atom, which is going to represent A, and then we have 1, 2, 3, 4, 5 bonding atoms, which means trigonal bipyramidal, and then you would set the structure up as to look like in the middle, or the way I've actually drawn it to begin with. Another shape that comes out of the exceeded octet is the octahedral shape. If we take a look at SF6, the 6 fluorine atoms will bond to the sulfur, creating 12 bonded electrons, or 6 pairs of electrons. So the code here is AB6. We've got the sulfur, which is the central atom, and we have 6 fluorine atoms. AB6, octahedral shape, 3-dimensionally, all of these angles are going to be 90 degrees. You won't have many of the octahedral shape or trigonal bipyramidal shape structures given to you. I just wanted to make you aware that they are out there, and there are probably about 6 different shapes in addition to these that if you were at an advanced placement level, you would be studying those as well. Now, what we haven't talked about yet are the lone pairs coming off the central atoms. They also have to be taken into account when determining the shape of the molecule, since they are electrons negatively charged and they are going to repel the other bonds as well. One caveat is that you want to remember that it's only the lone pair of electrons coming off the central atom that will be important in the code. There will always be lone pair of electrons in the Lewis dot diagrams, but for the code we are only looking at the lone pair coming off the central atom. All right, so let's take a look at the bent shape. We're going to actually take a look at two different codes here. The first one is of sulfur dioxide. Now, you probably would have drawn sulfur dioxide to look like this in your original Lewis dot diagram. So let's just look at it from that perspective. We've got an A, we've got two bonding atoms coming off of it, and then there's your lone pair coming off the central. So this is an AB2E. An AB2E is going to spread out into a bent or V-shaped. And so if you come over to this picture and I had to rearrange the molecule of SO2 to look bent, this is basically what you would see. Of course, there's lone pairs of electrons around these oxygens. There's about 120 degrees difference between the terminal atoms and the lone pair of this particular shape. In the second example of H2O, which is water, if you were to have drawn that using the rules, you probably would have drawn something that looks like this. And if we were to code this, we would say we've got a central atom, which is A. We've got two bonding atoms, there's your B2, and you have two lone pair for your E2. That will also give you a bent shape. And so you can see here the oxygen will go in the middle with the two hydrogen atoms bending down, and the two lone pair will take on the other two positions that are available. The angle between the lone pair and the hydrogen atom will be about 109.5. I'm hoping that these angles sound familiar. You'll notice that this is the trigonal kind of pyramidal shape if there were three bonding atoms. And then, of course, this would look like the tetrahedral shape if there were four bonding atoms. There are not four bonding atoms in this picture. There's only two. That's why it's bent. But there's still 109.5 degrees difference between the hydrogen and where that lone pair would sit. The last shape is the trigonal pyramidal shape, and that is also going to have a lone pair coming off the central atom. But this time it will have three bonding atoms. If we take a look at ammonia, and we drew ammonia out using the rules from section 5.2, you would have gotten this structure. If we code it, you've got a central atom, that's A. We've got 1, 2, 3 bonding atoms, that's B3, and you have one lone pair off the central, which is your E, and AB3E codes as a trigonal pyramidal. So we need to take the ammonia and we need to turn it into a trigonal pyramidal shape, which is what you basically see in the middle of the screen, but that's with the wedges and the dashed lines. So let me just give you a better way to draw this. We'll just take the N and we'll kind of angle down the hydrogens so that they kind of look like they are in a pyramid shape. So lone pairs of electrons aren't controlled by a nucleus on both sides, only on one side. So what that means is they can actually spread out more so than a bonding pair. And because of that, they tend to distort the angle of the molecule's bonds away from the lone pair. If we take a look at these two pictures, you've got the carbon tetrahydride, which we had looked at earlier on, a tetrahedral molecule, with a code of AB4. And we knew that the angle difference between the two bonding atoms was about 109.5. If we take a look at water, H2O, which we know is bent, and we look at its code, it's AB2E2. Looking at these two pictures, you might think that they are the same shape. However, they're not. The molecule on the left is tetrahedral and the molecule on the right is bent because it's based on the position of the bonding atoms. The molecule on the right actually has two lone pair of electrons taking place of two bonding atoms on the tetrahedral molecule. And that's why if you pulled those out of the picture, you would see that bent shape. But it still has its electron pairs in that tetrahedral shape where there's 109.5 degrees apart. However, we just said that lone pairs spread out a little bit more. And because they spread out a little bit more, they're actually pushing these two atoms a little closer together. And so it's going to be less than 109.5 degrees in angle or 105 degrees.